Hello. Hello. Hello, Raymond. Hello, Shen. Wait, this is where you do the hellos to me. You start the hellos. That's how this works. It helps me know if you can hear me now. Hello. Okay. Thank you. And that counts. Yes. Good afternoon, Louise. Thank you. Oh, here comes more people. Sorry. Okay. Thank you. So, thank you, Raymond. Thank you, Luis. Or hello, Raymond. Hello, Luis. Hello, Shen. Hello, Jay. There is the man. The other man. Hello. Hello. Thank you. Okay. I said that. Wait. Yes. So, hello, Shen. Good afternoon, Michael. Good morning, Jadith. Good afternoon, Danielle. Hello, Harris. Good afternoon, Michael. Awesome. Okay. Uh, Hola, ¿qué tal, Harris? Good afternoon, Montserrat. Good afternoon, Nico. And now we're rolling. Okay. Um, no more people. Oh, oh, okay. I guess, all right, that's a quorum. Just kidding. Okay. So, hello, Mantra. That's a good avatar. Hello. Oh, and there's wow, avatar and video in one day, in one 10-minute interval. And it was a new avatar. And there's Sophia with video. Okay, now I mean, I was excited before, but now we're like, okay, now we're happening. I mean, it is the afternoon. All right. So we've got Raymond, we've got Michael, we've got Mantra, we've got Sophia, we have Harrison Jadith, and we have and Shen, and we have Leah, Luis, Danielle, Nico, Lila. I mean, yeah, Lila. I have two different people with similar names in two different classes. Sorry. Yeah, and Lila, and the squares just moved, so I apologize. I think that's Montserrat and Joyce. Oh, and there's John. Yes, hello, Joy. Okay. Oh, got it with the other device. Okay. All right. So I'm just gonna start more. Okay, I'm gonna start rolling again. I mean, and oh, ta, 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 ta. Again, if there's any questions at all of anything, in fact, I'm gonna pause for a second because I'm not even gonna do all my this, that, and the other thing stuff. I'm gonna get straight to physics. So if there's any questions or concerns about other stuff, please let me know now. Good afternoon, Gerasimos. Awesome, thank you, Jerry. Good afternoon. Um, the okay, I will say one thing. Things are starting to move along now and get into, some material that is maybe not a joke, maybe. Um, you are expected, we're now at the realm, we're now in the zone of the class where like homeworks are going to get longer. You're going to have to think about them more, even before I say things about them. Where I'm going with this is the deal is as so like homework, what I'm saying is homework two, math methods. Technically that's due this Wednesday. Yeah, that's due this Wednesday. That means we're now at the realm where it, in order to of you want to turn in a valiant, thorough first draft using 5-step method on time for Wednesday. Like as long as it's a valiant, reasonable, thorough 5-step method attempt at a first draft of math methods 2 for Wednesday, then that means even if you don't get all the points right away, you'll be able to get all the points once we talk about it more and all. I know I keep saying this, but what I'm really trying to say right now that's new is we're now far along into the course enough that in order to get all the points on something, the first draft does have to be in on time. like then we could take our time with revisions, as many as we want, and you could wait until I say more things in class and all that. But basically, I'm saying all this because I know math methods sort of does a lot of these math things. Homework 2 picks up on stuff that we're just going to get into today. So you may feel by the time you're getting to math methods that some of this stuff is old calculus, or you saw a while ago in calculus, or some of it is things we haven't said a lot yet in class. Some of you will have to think. Some of you might even go on the web and refresh yourself. Some of you might help one another. I'm not expecting perfection. I'm not expecting perfection. I'm not. But I'm expecting a first draft attempt at homework 2 for Wednesday, even though we may not have finished everything we're saying about homework 1 by then. I'm expecting an attempt. As long as you make a thorough attempt, then even if you don't get all the points right, then that means you're in a position to get all the points. But conversely, if a first draft doesn't come in for when it's on time, then you'll still do it. You'll still get a lot of points, but you won't get all the points. Okay. Yeah. Okay. Okay. All right. So if there are, more people. Wow. Okay. So many. Oh, sorry, Michael. Yes, Michael, please. Yes.
Um, so I wasn't sure how, or not how, but I wasn't sure that if I had to do the 5-step method for the math problems. So I just kind of did it like answering the questions.
That is a very good question. Okay. Glad you asked. So the short answer, so actually the 5-step method really is meant for problem solving, whether it's like physics problems or calculus problems. In some ways, it's even more relevant to like calculus problems. However, so my short answer, or my first answer, is I actually am still expecting the 5-step method, believe it or not. However, well, however, if diagrams seem strange at first, and they will to many of you, at first you'll be like, what diagram am I supposed to produce? Especially if Yaverbaum didn't put a diagram in his sheets. Let me say, if I don't put a diagram in my sheets, that's almost all the more reason you need to make a diagram. It makes it harder on you, maybe, but that's why that means someone's got to make the diagram. For strictly mathy things like that homework, when in doubt, my advice is there for math problems, you think about graphs. Like, I mean, for example, you're going to see soon, if it's not already possibly in your mind, a lot of these things that we're doing right now are going to come down to cosine graphs and sine graphs, but really cosine. And I'm going to explain this more today. But when in doubt, when you're starting off a problem, I would suggest maybe a cosine graph. And to make a graph, the same objective applies as diagrams in general, which is it's really about the labels. Okay, so this quick sidebar, very, very good question. In physics, when we ask for a graph, especially if it's not raw data literally from an experiment, what we want is axes that are labeled like t, seconds, x, position, meters, something like that. We want axes that are labeled. We want a trend, a curve, a best fit of some kind. So it could be like, this is like a sketch. Like, you didn't do it in a lab. So say we're thinking about a cosine graph, like, just to sketch the shape of a cosine graph. And then maybe 1 or 2 key points labeled to represent the whole thing. So for example, labeling a y-intercept or something, partly so we could see what the y-intercept is, and also so that we can understand what scale to read this graph on. So I think, so first of all, so I am actually saying to everybody, yeah, the mathier it looks, the more it seems like it wouldn't be 5-step method. Like, again, this is a totally legit question. But the more mathy it looks, the more sort of we really need the 5-step method. So for diagrams, when in doubt, think graphs, like cosine graphs. Make sure to fully label the axes. Don't get bogged down in like connect the dots, but just labeled axes, trend, and 1 key or 2 key points. That's for diagram. Then absolutely you could do what is the question. You still doesn't have to be English. It could still be very much like the way I put it, but but what is the question? GDP, and again, I'm going to start walking through these. This homework too. I mean, I have to finish homework 1 first, but when I start going over it in class, you'll see how what I pick for my step 3 GDPs, and they tend to be definitions like definition of derivative or the derivative of sine is cosine, this kind of thing. Like that would be a GDP, that if y equals f of x, then and f of x equals sine of x, then dy dx equals cosine of x. I know I'm speaking very quickly, but things like that, definition or like fundamental like derivative rules or derivative definitions tend to be our GDPs for this homework. And then 4, do out all the computations, and 5, circle the answer. So long way of saying, yes, we do want the 5-step method, but even though I could see how it seems like we don't. But then also, if it starts getting the key really to the 5-step method is sledgehammer me with it at the beginning of a homework. Like in the first couple, absolutely, like go overboard with the diagram and with all the facts that might be relevant for step 3. Like go overboard at the beginning of the sheet, and then once it gets all exercisey and repetitive, which it totally does, then you can start streamlining and saying see above, and things like that. Your work can get streamlined as you go. And again, and this is true for exams as well. It's why I'm glad he's asking this question. I mean, I'll check back with him in a second. But so you don't have to, you don't have to do a million steps for a million. Once I get the idea and once you make it clear to me, then you can refer see above. But okay, that's a long, but okay, that's my basic answer. Does that make sense, Michael? Or do you follow up, or does that sort of?
Yeah, that makes sense. I'm wondering if you have YouTube videos from like previous semesters that when you went over that homework,
Oh, you're wondering if there are any, or whether you're allowed to use them.
if there are any of
Oh
like,
yeah,
maybe previous semester or 2 semesters
oh
ago.
yeah. That's another great question. Absolutely. So the good news and the bad, it's mostly good news. Yeah. There, and I would always, yes, I'm sure I walked through that homework, and I mean, it would be in a playlist. I would look in the most recent playlist first. I mean, I know I did. I mean, the answer is yes. Some videos are better than others for sure. But yes, I would go to the most recent playlists first. So like, wait, it's fall. So I didn't teach this summer for the first time in a while, but definitely spring. So look for playlist jjP204 SP24, meaning spring of 2024. That playlist, I would look there first. For sure, and I forget the title of the video. I mean, you have to like do it. So the bad news is you have to find it on your own, but I think it's pretty easy to find. Like I tended, I think I labeled I think I titled the video like homework 2 or whatever, something like that. So they're there. And if you don't see one from last semester, go to a playlist from the semester before. It's definitely there. And definitely legal to look at those things while you're doing the homework or before you do the homework, for sure. Yes. To everybody. Great point. And yeah. What was I gonna say? So, but all of this, but again, I'm glad he's asking. All of this is to say too, between the old YouTube videos, or between that I'm answering this question in class, or between what we're going to say today about the end of homework 1, you should definitely have enough to go on that you can try homework 2. I mean, more than try. You should be able to have a lot to say about homework 2 by Wednesday, even if at the end you think certain of your answers you're not confident about, or certain calculus you don't remember. The part of the flip side, and I know the flip side to Michael's first question, like the bad news is, yes, you do have to do 5-step method. But yes, sometimes you have to be sort of clever about it when things look very mathy. That's the bad news. But the good news is, what I'm really saying to everybody is that once you get used to the 5-step method or something like it, you start to realize like the first 3 steps of the 5-step method, the first 3 steps are like happen before you even are doing anything in solving the problem. Like the first 3 steps are all like set up for a reason, which really means Once you start trusting yourself and trusting this, at first the 5-step method looks like a lot of extra busy work. I know that it does. It looks like a lot of annoying extra busy work when you can just see things in your head and they look quick. But already in homework 2, we're getting to the point where some of those questions for some people, they might look like quick exercises, but people don't know how to do them. And you shouldn't be ashamed of yourself if you don't remember how to do them or you don't know how to do them. But the thing with the 5-step method is it gives you a lot of crap to, it gives you a lot of stuff to write down even before you know what to do. It gives you a lot of things to write down to like set things up and get you ready to solve things so that you get. So basically, for some of you, if you look at this and you're like, oh my God, calculus, like I hated calculus when I took it and I failed it twice. And then like and then whatever, I put toilet paper all over my math professor's house. Like I'm traumatized, but I don't, even if you feel all bad about calculus, I'm kind of trying to tell you that you could take out, not you, not Michael, like everybody. I'm trying to say that you could take out your homework and just by trying to follow the steps on most of the problems, you would end up writing so much that when you hand in for your first draft, even if you never got good answers or answers at all, I would totally regard it as a substantial first effort. Like, so that's the way. So it's trying to teach you how to write things down, even when you don't think you know what you're supposed to be writing things down. And then the steps will get you to more and more things that you can write down. But okay, again, way too long of an answer to totally legitimate questions. But so I'm saying, yes, totally look at old videos. Yes, I walked through, I'm sure I did. Well, I know I did walk through homework 2 in the playlist. jjP204 spring 24. But yes, please do the 5-step method. Consider it your friend when you don't know what's going on. It gives you a way of making progress no matter what. Okay. So even when things, okay. Does that, sorry, does that all answer? Does that make sense?
Yeah, perfect. Thank you so much for your time.
All right. No, thank you. Thank you very much. Okay. Awesome. Um, Okay, so I'm going to shift gears now, but again, honestly, just want to remind you too, when this is my ideal version of the class, folks. My ideal version of the class is that before I get rolling with physics, we get like concerns addressed, and it's ideal if they come from you, not me. I just want to remind everybody again that not only can Michael now get points or whatever, and it's not about Michael, I'm just using him as a good example. Like, I just want you to know that whatever just happened between Michael and me in the first 10 minutes of this class, that is not, oh, they're off the topic. Now let's do class. That is class, right? Like, that's the point of class. I prefer it when people feel comfortable asking things like that before I get going. It makes me feel more secure that where we're going could make sense. Okay. So part of the reason I do all this hello, professor stuff, part of the reason I like it, that you all say hello in the chat first. First of all, it lets me know you can hear me in the videos working, all that. But then also, really, the beginning of class is a good time to get these kinds of concerns addressed. It's not off the topic, it is the topic. Um, so please, if anybody else has any questions like it, don't feel like you're interrupting. You're like you're not. But if not, now that he's broken the ice, I'm not gonna. We'll turn the page. If that's it, I'm gonna start going back to. But I'm looking at the chat. If that's it, okay. I'm going back to. Yeah, I'm going back to homework 1B. Back to Lila's question from last time to question 6 is where we're going today. And I know I keep promising that I'll go back and expand more on like questions 4 and 5. I'd like to do that still, but I feel like since we're now making progress and since you at least have answers and a skeleton for questions 4 and 5, I really want, or question 9, so now I'd really like to really get into the meat of question 9. And if we have time, then we'll go back and expand on 4 and 5. I'm going to go into the meat of question 9. And everything I'm about to say now everything I'm about to say, well, is to lead up to what's on the board right now. Like what's on the board right now is the conclusion that I'm going to try to show you today. I'm trying to get to. I'm not assuming what's on the board right now. I'm about to try to teach it. It's the way to get the answer to question 9, but it's also like the big for the material for the rest of this course. Um, Okay. So just reminding you, first of all, okay. Hold on. Just something in it. There's just direction. There's a bunch of things in the direct chat. Okay. So reminding you, the question 9 is, we got the mass on the spring. We've been drawing it a million times. And technically the question is, at t equals 1, what is x? Like how far into the motion is the mass at 1 second? But now the first thing I want to observe is really what we're really asking, what is x as a function of t? We're really just asking, what is the relationship between position and time for a situation like this? And what do I mean by a situation like this? So I'm saying my goal here, yes, my ultimate goal is to get a number, like literally numerically where the mass is. But really, honestly, for the rest of physics time, what my real goal is, can I set up a relationship between x and t for a situation like this? And what do I mean by a situation like this? What I mean by a situation like this is one in which, well, F equals ma, which it always does, and one in which a restoring force is being exerted on a mass by a spring, right? This is the situation. What just happened? Why? Oh my God, why is it? Oh. I'm going to change. I can see this color is not, I'll get a lighter color in a second, but I'm just reviewing what we said last time. Like the issue is that Hooke's law is governing uh the motion of the mass on the spring. And I'm reminding myself before I go any further that the definition of instantaneous acceleration can be defined in calculus terms. Instantaneous acceleration is the derivative of the derivative of position with respect to time. So those are my three big GDPs. Um, Okay. Well, that's good. Where we left off last time. What I kindly, yes, sorry. Tell me when I can. So I'm technically sort of reviewing where we left off last time, but I'm saying our goal here, the real problem, the real what is and this is another advantage of step two. What is the question? Step two. The question is when t is one, what's x? But I'm saying now that we're getting more into physics, really, when I really think about that question, what that question's really asking is given t, find x. Like it doesn't really care about the one. By the time I get any kind of relationship between x and t, I can just plug in one for t and I'll get an answer. And if it were some other value of t, I get some other answer. So I'm really trying to get x, what is x as a function of t when f equals negative kx? That's like really the issue here. When something's oscillating back and forth, in fact, let me even write it that way. Like I'm saying, the real question here is when something oscillates, go back and forth, moves cyclically. When something oscillates according to the law of elasticity, like Hooke's law, then how can we relate where it is to what time it is? That's where our real issue is here. What does a so I'm going to go back. Oh, good. Thank you. Okay, great. So I did a little bit of substitutions from the GDP. I put the GDPs together in step 4. I'm starting to put the GDPs together. And now I have an equation, d2x over dt squared equals negative k over mx. So it looks like I'm getting somewhere because everything that's in the parentheses, these are all constants. These things may look like letters, K and M, but they're really just letters that stand for numbers, i.e., the numbers don't change. Like K is throughout this whole problem 200 newtons per meter, M is 0.3 kilograms throughout the whole problem. So they're not variables. They might look like it because they're letters, but they're not variables. They're constants. They're not right. They're not unknowns, and they're not varying, changing from time to time. The only variables in this expression are x and t. And the way the expression is being written, the fact that x is in the numerator of a derivative expression means x is something that depends on t rather than the other way around. So we've got an equation here that's treating x as a dependent variable and t as an independent variable, and there are no other variables in it. So this equation has all the information we need to solve for what we're looking for. It has all the information we're looking for of x as a function of t. Only the packaging is not the packaging that we want. Like I literally want x equals blah, 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 times t. I don't want d2x dt. So I've got to solve this equation that we now have. It's correct. It's it's correct, but it's not in the form that tells us what we need to know. This Okay. Notice. I want you to notice two things that maybe take like side notes on this. The first like thing is we're looking for x as a function of t. We're looking for a dependent variable as a function of independent variable. First thing about what we have here is it doesn't give us that. It gives us derivative. In this case, the second derivative. It doesn't tell us the variable. It tells us the rate of change of the rate of change of that variable. That's a first issue. The first reason we don't have an answer yet, or that we're not done, is we're looking for x, but we have instead a second derivative of x. So we have an equation that has a derivative in it. So we have to do something about that. But the second thing, the key thing that you may want to write more clearly in your notes than I did right here, the second thing, the really subtle but hugely important thing, is that this derivative here is being presented as an expression of, or as a function of, or as depending on x itself. Like what I'm really trying to say is look on the right side of this equation and notice that there's an x, not a t. That is a huge deal. And it's for that reason, like the fact that what's on the right side is an x, not a t. The fact that what's on the right side is the dependent variable, not the independent variable, is what makes this thing known as a differential equation. Now we have to dwell on this for a few minutes, but really for the rest of the semester, but this is a differential equation. We have to solve it. First of all, I'm not, and that's a lot of physics is a lot of physics is devoted to the solving of differential equations. It's a big topic in math, differential equations. There are whole classes, many classes devoted to the solving of just that, differential equations. First thing I want to say is you are not expected to have taken a class in differential equations before this one. I want to make that very clear. We are going to make a big point about differential equations. They're inescapable from this level of physics. I also love them, but don't, and you could be a little scared if you want or whatever. You could like buckle in your seatbelts, but don't think for a minute that I think you've already learned this. I do not think that. I don't expect that. What I expect is that you've learned enough calculus that this can be the next step that we can learn together to the extent that we need it for here in physics, right? Like, just like when you're in physics 204, I don't expect that you've already taken physics 204. I do expect that you've taken physics 203, right? Like, not to be dumb, but we have to get into some serious calculus in this class. I'm expecting that you've seen derivatives and seen integrals enough that you know what they are and that you're willing to sign up and deal with them with me, even derivatives and integrals. I'm going to explain more. That's every time I say I'm going to go back and expand on parts 4 and 5 of the old homework, what I really mean is I want to like lay out integrals for you so as a refresher, whatever. And some of you don't need that, and many of us do. I expect that you've seen derivatives and integrals. I don't expect that you love them. I don't expect that you're masters at them. Maybe some of you are, but I don't expect that. I expect you've seen them enough that you can go forward with me into the next steps. And this next step is something called a differential equation that we're going to learn about together, like right now. So that's the first thing is, but I want you to know you're learning it too, because those who go on in science and stuff, or certainly PChem, like this is a huge part of PChem is this equation and equations like it. So I want you to buckle in your seatbelts a little and realize, like, if you've ever heard of differential equations, that's what we're going to on a science level right now. So the first hallmark of a differential equation, the first characteristic identifier of a differential equation is that it is more than just an equation with a derivative in it. I mean, yes, it is an equation that has a derivative in it. Yes, the first issue that we're facing here is we wanted x, but we're getting an equation that expresses d2x dt squared, right? Yes, but specifically, what makes this equation a differential equation It's not just that it expresses a derivative. It's that it expresses the derivative as a function of the dependent variable. That's interesting. Let me try to put that, and it's unusual. I mean, it's a whole phenomenon unto itself. Let me try to put English to that for a second. Like, you could think of independent variables sometimes as like cause. And again, this would be a good place if you want to write. I don't want to get myself into a rabbit hole, so I'm trying, but you might want to write this down. Like, often we think of independent variable as a cause, and we think of dependent variable as like an effect, right? Like the independent variable drives the dependent variable, right? Like, however, in science class, in math class, whatever, in life. A differential equation says that some kind of rate of change of effect with respect to cause. So I'm reading the left side right now. Like, what is a derivative? A derivative is rate of change of effect with respect to cause. Like if you look at the left side here, we're talking about the rate at which position changes in response to time, right? The left side of this equation is asking you to look at, it's actually the rate of the rate, right? It's like not velocity, it's acceleration, but don't even get bogged down in that right now. I'm just saying that the left side of the equation is making a statement about the rate at which position changes in response to time. But then the right-hand side says that it's dependent. Like, if you want to know the rate at which the mass is accelerating here, the right-hand side says, well, it depends on a variable. Like, of course, all equations are. One variable depends on the other. One variable is in response to the other. All equations, right? The right side has this sort of surprising feature that says the rate at which position changes in response to time depends on not time, but position itself. This, like all differential equations, this one's saying the rate at which the effect changes in response to cause depends on not the cause, but the effect itself. Please let that sink in for a second. That's a deep idea. I'm not saying we can't handle it in this class. We're going to handle it. But the reason there's like all kinds of classes on this and stuff is it's actually a deep, weird idea. It's actually amazing that we could ever solve an equation that has that structure. Because we're saying, I'm going to say it one more time. It's like, it's literally, okay, quick example. I'm getting myself all, but quick example. Wait, this ends at 420. Yeah. Quick example. It's like if I go into the bank and I ask, hey, yeah. I go to the bank. I have a bank account and I have like an interest-bearing savings account. So I get more and more money as time goes on, right? Like I put money in the account and it bears interest. So money is a function of time in my bank account. The more time that passes by, the more money I have in my account. So this is very hypothetical, very hypothetical. But so say one day I walk into the bank and I'm like, hey guys, how much money do I have in my account today? And they say quite reasonably, well, actually, that depends on how much like interest we just put in last night, right? So they say like interest is like the rate at which your money changes in time. So to answer your question, we would have to look up, or we have to know how much money we added to your account last night. How much was the interest? Okay, fine, that's reasonable, right? So interest is like the rate at which money changes as a function of time. So I say to them, oh, okay, fine. Like, how much interest did you put in last night? Like, okay, like, what money did you put in the account? And what would they say? They would say, well, I don't know if everyone knows where I'm going, you could feel free to answer. But if it's an interest bearing savings account and I say, how much interest did you put in last night? They're going to say, well, that depends on how much money you have in there, right? The amount of money gain per time doesn't just depend on time, it depends on money. If the change in the effect doesn't just depend on cause, it depends on the effect itself. It's like feedback loop. It is. It's like a circle. That's what we're saying. And in English, in this in this problem, what I'm saying is we're very used to physics situations and equations that care about acceleration. The reason we obsessed about acceleration so much in physics 203 last semester, because of the belief that if you know the acceleration of something, then like you can do something like x equals 1/2 at squared plus v naught t or something. As long as you know the rate at which something is accelerating, you can predict where it's going to be at a certain amount of time, right? If you know that was the assumption of last semester. So here, like I'm trying to predict where this mass is going to be in a certain amount of time. So the first thing I want to know, just like from physics 203, is, well, okay, what's its rate of acceleration? If I want to know where the mass is, I'd like to know its acceleration. Just like if I want to know how much money is in my bank, I need to know how much they added to my bank of money, like every minute or last night or whatever. But the catch is that in a mass on a spring, if I say to you, hey, where's the mass? And you say to me, well, that's easy. We just need to know the acceleration. Evidently, I then, according to this equation right here, I say to you, oh, well, the acceleration depends on where the mass is. But that's what we're trying to freaking figure out. Okay, I don't want to beat I don't want to beat this to a dead horse. I don't want to beat this up. But I am saying, before I go any further, what I want you to know is a differential equation is not just an equation with a derivative in it. A differential equation is an equation where the derivative is presented as a function of the dependent variable, which means like rate of change of effect is being expressed as depending on, it means that the rate of change of the dependent variable is depending on the dependent variable, not the independent, the dependent. That's kind of crazy, but it's true if you think about the physics here. The question is, how can we break that apart? How can we break that apart and get any direct information about position in relation to time? If we could find a way to break this thing apart somehow and actually get x as a function of t, that would be solving the differential equation. Okay. What we have to do now with the 27 minutes left, we want to solve this differential equation. To solve it means to come up with an x equals f of t that fits this equation. One that, so we're going, in other words, the solution to this is not going to be a number. The solution is going to be a function. And we sort of have to work backwards. It's kind of like Jeopardy. Like, this is the answer, this differential equation. We need to figure out the question, or that's not a perfect analogy, but we need to find an x. I can go back in a second if you want. But Okay, so what we're looking for, we're gonna, so, and I wrote off in the margin for it, this is essentially puzzle solving. Like, I'm making a big deal of this because it is a big deal, and also because I want to sort of prepare you for the fact that we're going to solve this, we're going to get a solution, but it's not a linear process. This is another reason why that 5-step method is like really useful for us in contexts like this, because this is not, what I'm about to do is not like taking derivatives where you have strict rules and you just, it's a product of two functions, so I do the product rule. It's the power rule, so I lower the power, and I'm like, this is what we're about to do is backward thinking. We're not just taking derivatives. We need to find a function of x, excuse me, we need to find an expression for x such that when you take two derivatives of x, when you take the derivative of x with respect to t and then you take it again, you get back what the equation said. You get back negative k over m times x. In other words, we want some x that when you take its derivative twice, you get back x itself somehow, which sounds weird. We want an x that when you take the derivative and then you take the derivative again, you get back the original x, but times k over m times -1, like the original x times a certain negative constant. That sounds weird. I mean, to me anyway. I mean, I don't want to make it weird for you if you're cool with it, but we're not taking the derivative of something. We're looking for something for which, when you differentiate it two times, you get back a version of it. That's what we're looking for. And that would be true in any differential equation. Just the specific version here is that it's two derivatives we're going to take, and what we're going to get back is the original expression times k over m times -1. So I'll start moving this along, cutting to the chase. We're going to go backwards. There's no clear forward procedure for doing something weird. Like, why can we not just make a clear forward linear like algorithm for doing this? Because what we're asking ourselves to do already is a strange thing. We're like cause and effect are being reversed here. So the order in which we have to think has to be sort of reversed. That's not really an explanation, but it's true. So what we're going to do, in other words, sorry, okay. So we're going to guess and check. We're going to think of a function. We're going to build a function that we think might be reasonable or plausible or might be right. We're going to build that function from our understanding as scientists, for the fact that we've been in the lab and we've looked at masses on springs. We're going to picture what the graph from, like, we're going to picture a mass going back and forth on a spring, or a mass going back and forth on a spring. Imagine, measuring where the mass is at regular intervals of time. Like, where's the mass at t equals 1? Where's the mass at t equals 2? Where's the mass at t equals 3? And then imagine taking that table of values and turning it into a scatter plot. What would the scatter plot look like? We'll use our picture, or we could literally run the experiment if we want. We would look at the scatter plot and the trend line from our data and say, oh, this looks like a certain mathematical function that I think I'm familiar with. I'm going to guess that the answer to this is that mathematical function. I'm going to guess based on my living in the lab. Guess. Guess doesn't mean it's right, but it means it's a starting point with a basis. And then we're going to use calculus to verify, to put the details on that guess and verify for sure whether the guess is correct or not. I.e., if we were to go into a lab, I know for some reason these colors look really light today. Maybe they always do. I mean, really, they look really dark. I mean, if we went into a lab and we put a mat, like we picture this problem one, but turned into a lab. So we have the mass sitting at an initial value that we call x naught, or in this case was like 15 centimeters, and we let it go from that initial value. It would start heading in toward the equilibrium position, just like all of our answers to homework one, but it would have a lot of speed when it gets to equilibrium. So it would keep going all the way to the other side. Then it would run out of speed. And then it would come back and right. It would go back and forth and back and forth. And so if it started at some value like x naught, it would, right? I mean, at t equals 0, x would be x naught. So that would be an initial value, but it would start heading towards 0, but going faster and faster and faster. So steeper and steeper and steeper, start heading towards 0, but it would keep going when it got to 0, it would cross through and start heading to the other side, and then go slower and slower and slower until it had no velocity, or until the slope of this graph was 0, right? So then it would start turning around and heading back, et cetera, et cetera, et cetera. And of course, I mean, I think the graph would look something like this. The graph does look something like this, like back and forth and back and forth and back and forth, but smoothly. So no jagged line, no skipping space, no discontinuities, no straight line, no corners, because corners wouldn't be smooth in nature. Like these don't have corners, because that corner would mean it would run out of speed in 0 time whatsoever, and then turn around going the other way at a maximum speed in 0 time. But that's not possible. So it'd be the smoothest possible version of going back and forth, back and forth. That graph looks something like this. And this looks like some kind of cosine. Now this is a guess. Just because I'm guessing it doesn't mean it's right. But just because I'm guessing it doesn't mean it's not math. Like a guess doesn't make it right. But a guess is not illegal in math. And everything I'm showing you right now, really quick, about how to solve these kind of differential equations, this isn't a physics cheat or a cheat because you've never seen them before. Saying this is how a lot of differential equations have to be solved, from guess and check. Because just like with integrals, if you really think about it, derivatives you could do straightforwardly, but integrals, you have to know techniques that have worked over time in the various puzzles of integrals. And some of the techniques don't work, and some integrals can't be solved. This is like that. This is much more like, and an integral is like doing a derivative backwards, and this is like doing a derivative backwards. It's not an algorithmic process. You have to guess. Just because you're guessing doesn't mean you're right, but just because you're guessing doesn't mean it's not legit math. It is legit math. In fact, real math looks like this. As long as we use real mathematical rules to prove in the end whether our guess is right or wrong. The guess is just a starting point. So this is my guess, is that the function that best describes x as a function of t is some kind of cosine function, some kind of cosine function. Note real quickly that I'm saying cosine, not sine. Like, I mean, you could say sine, but the reason I'm saying cosine, if you're ever going to memorize anything from trigonometry, I mean, I'm a big fan of the unit circle. I love the unit circle. Like some of my best friends are the unit circle. I love the unit. And if you want to know the whole thing, that'd be terrific. But if you don't but if you're just going to know a piece of the unit circle or just something to hang your hat on, just know sine of zero is zero, always. Sine of zero is zero. Cosine of zero is not zero. Cosine of zero is one, right? Like people, and everybody knows that cosine and sine, not everybody knows, people tend to know that sine and cosine are related, but they sort of get them confused which one is which, whatever. Sine super, cosine crappy, or sine super, cosine counterintuitive, whatever, or cosine crazy, whatever you want to say. What I mean by that is the sine of zero is zero, just like you would want it to be. And when you open up an angle, when angles get bigger, sine gets bigger. Like, so if you were to make up one of these functions on a desert island by yourself, you'd make, if you're like me, sine is the one you make up. Sine is sensible. Sine of zero is zero. As the angle gets bigger, the sine gets bigger. Cosine is the one that's the opposite. Cosine of zero is one, is a maximum value, right? And then as the angle gets bigger, the cosine gets smaller. So this graph, if it's starting at a value other than 0, 1, sorry, if it's not starting at 0, 0, this is a cosine. And physically, what I'm saying is, if I'm thinking what's the best way to describe a mass going back and forth on a spring, cosine comes to mind because the mass starts out here at a maximum displacement and then it goes back and forth from there. That's all I'm saying. So my guess, I'm watching the clock. My guess is that it's a cosine. That doesn't prove anything. But not only does it not prove anything, also I'm saying some kind of cosine. Like what? Like I'm saying it could be something multiplied by cosine. It's some kind of cosine of t. But I'm leaving these blank spaces because I think there's going to be some constant. Like, I don't think that's the final answer. If that's the final answer, how did it use K and M? Like, K and M are two constants in the original experiment that clearly matter, the stiffness and the mass. This by itself doesn't take into account any of the constants. The reason that we left space for constants is the very same reason that's going to let us figure out what those constants are. This is all based on science in the physics, right? It's not just a random math problem for out of nowhere. This is all we're trying to analyze what's happening through space and time of a mass on a spring. We're making measurements, at least in our mind, if not in reality. So we got to consider units. Units of measurement, I mean. Like for starters, Okay, remember, or note, you can't take the cosine of a second or of a meter for that matter. You take the cosine of an angle measured in radians. Oh, what's the word? Near bad. Near bad. Between probably. Yeah, my handwriting is terrible here. Wait, which word? Near bad. I don't think I actually wrote bad. All right, so I'll just read this out loud. We cannot take the radian. Yes, radian. Oh, yes, radian is definitely what I'm trying to say. Yes. Thank you. Like I'm saying, you have to take the cosine of something measured in radians, an angle. I mean, you could do it in degrees, but from here on in, we don't do degrees. We'll talk about that next time. But radians are what we use to measure angles. Oh, cool. Thank you, Abdul and Shen. Thank you. That's multiplayer co-op right there. Thank you. So we measure angles in radians. You could take the cosine of something measured in radians. And then when you do, you don't spit out a radian or spit out a meter or a second. You spit out a dimensionless number, like a number between -1 and +1, just a pure number, right? So if we think about that, if we think about the units there, I'm saying first, what just happened? We can't take we can't, the answer to all this can't be x equals cosine t. It's got to be x equals cosine something multiplied by t. I don't know much about what that something is yet, but I know it's got to be measured in radians per second to cancel out the seconds of the t. Radians per second is some kind of rate of radians per second, some kind of angular, like it's not a rate at which you're pushing through meters in time, it's a rate at which you're pushing through angles in time. So we're ultimately going to call that angular frequency, but in terms of letters, we're going to give it a letter called lowercase omega. I mean, the Greek letter omega. That you could call it whatever you want, but this is what textbooks and stuff call it. And I'm not, and I'm teaching it right now. Like that's just a name for something that's got to go next to the t in order for the units to be right. But then similarly, so then we take the cosine of that. So we're going to take the, in other words, so far we have x equals blank cosine omega times t is what I'm saying so far. Omega is just a placeholder. I don't know much about it, but I know that it's got to be there to cancel out the units of t and leave radians. Then we're going to take the cosine of that. And what are we going to have? Some number between -1 and 1. It's just going to be a number. But the left side says that we need something measured in meters, right? And whatever is measured in meters, we want to range. I'm saying our guess here, I know we have 4 minutes. Our most complete guess here, it's still a guess, it hasn't been proven. But our most complete guess is to guess x equals x naught cosine omega t. Where did I get that x naught from? Because cosine will spit out numbers that range between -1 and 1, just pure -1 and pure 1. We want numbers to range between like negative 0.15 meters and positive 0.15 meters or whatever. We want, i.e., we want it so that when t equals 0, when the whole thing starts, x isn't +1 nothings. We want x to be positive 15 meters or whatever, right? So we put an x naught in front here so that when t equals 0, x equals x naught, and it's measured in the right units. Now we have 3 minutes left. I know I said that a little bit fast, but I'm saying just based on units alone, based on thinking about this scientifically, picturing the lab, and then thinking the units, we've come up with a conjecture, that the proper way to describe position as a function of time when we're oscillating back and forth is this x equals x naught cosine omega t. How do I know if that's right or wrong? I'm going to do this fast, but this gets you right into homework 2 and all that. How do I know if it's right or wrong? I mean, once I set it up, you'll see. To test, we now can take derivatives. Like to test, take derivatives. Why do I say derivatives? How many? 2, because it's a second derivative that we were looking for in the end. I'm going to do this really fast just so you can see. We'll expand more on Wednesday. But look, if x equals x naught cosine omega t, if I remember my trig derivatives and I remember chain rule, I would say dx dt equals negative x naught omega times sine of omega t. I know I'm doing this fast right now. I just copied for right now so you can see. I took a derivative. I did a trig derivative with chain rule. And then if I take another derivative like of that, I get negative x naught omega squared cosine omega t. We have 1 more minute and like 1 more line. Now multiplication is commutative, so I can rearrange that. I could say that's negative omega squared x naught cosine omega t. Like, so what? What does that prove? What does that have to do with anything? Who cares? Well, I wouldn't care, except look. And I know we have 1 minute. Look at this part right here. X naught cosine omega t. That is x according to our original conjecture, right? So apparently we've just come up with an x, which if you differentiate it twice, you get back itself times some constant times a negative sign. What was our goal? Our goal was we wanted the second derivative to be a negative sign times some constant times the original x. So our guess for x, we have still 30 seconds. Our guess for x is correct. When you differentiate it twice, you get back itself times some constant times a negative sign, as long as I'm just leaving on this page so you get notified. It's correct if and only if k over m means the same thing as omega squared. If that omega that we just made up for unit's sake, if it is the square root of the spring constant over the mass, then our guess was correct. Bottom line, because I know we're done, I'm saying from here on in, the differential equation that describes a mass on a spring is solved with x equals x naught cosine times omega t, for which by omega we mean the square root of k over m. So if you plug in 200 for k, 0.3 for m, 1 second for t, and 0.515 meters for x naught, put them all together and take the cosine on your calculator in radian mode, you get an answer to this question, which is 0.116 meters. Like, that's the answer point. But what I'm interested in, because we're done, is this solution to this differential equation. That's like really the purpose of the problem. Obviously, we'll talk more about that on Wednesday, but that's where I got the cosine from. And that's what math 2, homework 2 is all about. Okay, sorry, I went over. So I'm done. I'm turning off record, but you could stay and ask any questions or whatever. But other than that, have a nice day. Do homework 2 for, oh, thank you so much. See you Wednesday. Right. And do homework 2 for, awesome. Thank you.